Hello everyone. In this lecture, we will cover additional method for finding roots of nonlinear equation with single variables. In the previous lecture, we discussed the bisection method. Fixed point iteration is another numerical method used to find the roots of a functions or an equations of with the form of f of x equals 0. In this method, we first rearrange the function of the f of x to the x equal gx. Note that this rearrangement is not unique. There can be multiple ways to write the same equation in this form. After we rearranging, the next step is choose the initial guess, okay? And we show by x sub x. To find the next value of the x sub 1, we simply plug this value, is meaning we plug the initial guess into the function of the gx. And now we find the value of the x sub 1. Then we take the value of the x sub 1 and plug to the gx, okay, and we get the x sub 2. We continue this process and in general, we can write the formula in a general way. X sub n plus 1 equal g x sub n. And this is the main formula used in the fixed point iteration method to find the solution of the equation of the f of x equal 0. This iterative process can be stopped when either of the following condition is met. Once the change between the successive iterations or iterative convergence is smaller than a tolerance that defined by user, or once the mm, residuals is meaning the absolute value of the function at that point is smaller than the tolerance. And this is the two criteria to stop the iterations. The fixed point iteration method is a key idea we will use to solve the linear system of equations iteratively, and we discuss about it in the next chapters. Let's look at one example to see how the fixed point iteration is working. Look at these functions. This is the f of x that we have, okay, and the roots of these polynomial functions is one of the roots is 1.61, and this is the next root. This is the two roots of these functions, and now we are trying to find the roots of these functions based on the fixed point iterations. Again, the f of x for this problem, x2 minus x minus 1. Okay, the first rearrangement is write the x squared equal x plus 1. Note that this x, okay, the coefficient should be 1 and also the power of, should be as a 1. For this reason, we have to divide to the x and the answer will be 1 plus 1 over x. And now we can say this is as a gx based on the fixed point iterations. And we can write in a general format xi plus 1 is 1 plus 1 over xi. Now, for these parts, the initial guess is given, and the initial guess is 1. For finding the x sub 1, we plug the initial guess to these functions, or in this formula. We have 1 over, the answer is 2. For finding the next x or next iterations, we plug the x sub 1 to the functions, because we have to continue this process to find one of these roots. This is 1.5. See, it's become close to these roots, and we will keep continue this process. And it's meaning if we will continue, okay, our answer converge to this root. Okay, will converge to this root, but not as an exact value, but by some amount of tolerance, we can reach to these roots. The next rearrangement for these functions is rewrite this function as this format. X equal x squared minus 1. Now we can say this is the gx for this second rearrangement. And if I write general formula for this rearrangement, we have x2i plus 1. Sorry, minus 1. The initial guess for this rearrangement is given as a 1. Now we plug this initial guess to these rearrangements to find the x sub 1. Answer is 0. Minus 1. Minus 1 squared minus 1 is 0. X sub 4. As you can see, once we iterate or once we continue this process, okay, the answer oscillate between the 0 and negative 1. And we cannot find one of these roots, okay? For this reason, by this rearrangement and with this initial guess, we cannot find these roots. Let's look at another rearrangements, okay, for these main functions. Another rearrangement is write the x as a 1. Again, the coefficient and order of the x in the left side should be 1. Is 1 over x minus 1. Now this rearrangement for fixed point 4, and this is as a gx. This is the general formula for this rearrangement. For these rearrangements, the initial guess is given as a 0. Now we plug to this formula and try to find one of the roots of these functions. Once we plug to this formula, the value of the x1 is -1, the value of the x2. Again, we will continue these iterations to find one of these roots of the functions. The value of the x2 is -1/2. And if we continue, for example, the value of the x sub 3 or the value of the x for the third iterations is -0.6, -0.625, and continue. As you can see, once we, by this rearrangement and with this initial guess, once we continue, we can find, or the algorithm converge to this root of the functions. It meaning this process converge to the root of the -0.61898. Is meaning between these theory rearrangement and initial guess, just by these two rearrangements, okay, with these two initial guess, we can find the roots of mm, these functions. This is about the fixed point iterations. Let's look at another examples related to fixed point iterations. Okay. Find roots of these equations by using the two different initial guess. The first step for finding the roots of this function based on the fixed point iterations is rearrange the functions. This is our functions. Now we can rearrange as these formats. Okay, this is one of the form of the rearrangement of the fixed point iterations. Okay, as a general, the roots of this function is a 1 and another rearrangement for fixed point iterations, okay, is this formats, okay. And as I mentioned before, the rearrangement to fixed point form is not unique. This is the second rearrangement, okay, for these functions. And also we could have written these functions, okay, as this format, and this is the third fixed point form for these functions. Now we are picking, I'm going to choose the first two rearrangements or two fixed point forms, okay, and investigate with two initial guesses, meaning 2 and 5. Okay, this is the first two rearrangements of the function g1 and g2, and this is the initial guess. Okay, initial guess 2. Once we once we plug the initial guess 2 to these rearrangements, after each iterations, as you can see, the answer after each iterations, okay, the answer close to the roots of these functions because we know that one of the roots of this function is 1 and another is 4. For the second rearrangement with initial guess of 2, with each iterations, the value of the x, okay, approach to the another roots of the functions. As you can see, after 10 iterations, the value of the x is 3.945, is close to the roots of 4. For, okay, this is about, again, we are using the same same first two rearrangements. Okay, now just we are changing the initial guess from 2 to the 5. As you can see, for the first rearrangements, the value of the x by each iteration is increased. And after 10 iterations, the value of the x is reached to the 5 times 10 to the 25th power. This shows that this solution diverges and does not approach any of the function's roots. On the other hand, for the second rearrangements with the initial guess 5, the value of the x, okay, after each iterations is converges toward to one of the roots of the function, is meaning number the root 4. As you can see by two rearrangements um, and two different initial guess, okay, one of the two initial guess, sometimes our solution converges to the roots and sometimes it not converges, okay. For this reason, this condition is happened for the fixed point iterations, and we have to know that how can be sure our rearrangement and initial guess will actually converge. To ensure convergence, we use the fixed point theorem. This is a sufficient but not necessary condition for the fixed point iterations. According to the theorem, the absolute value of the g prime x at the initial guess should be less than 1. Let's let's check the fixed point theorem criteria for the first fixed point form, okay, by using the two initial guess, okay. This is the first fixed point form for the previous problems, and now we are checking for these two initial guess. The derivative of the gx is 2 over 5 times x, okay, and once we are evaluate at this initial guess, the value is less than the 1, and this means the algorithm converges to one of the function's root with this rearrangement and this initial guess. And as you can see, after 10 iterations, okay, we find one of the roots of the function. How about the initial guess 5? The value of the g primes is mean the derivative of these rearrangements, okay, at this initial guess is greater than the 1, and in this case, the algorithm diverges. And as you can see, after each iterations, the value of the x is increased, and after 10 iterations, reach to the 5 times to the 10 to the 25th power. How about the second rearrangement? For the second rearrangements of the um, second fixed point forms, the derivative of the gx is this equation. Now we are evaluate at these two initial guess. Once we are evaluate the g primes, okay, at this initial guess 2, the value is greater than 1, okay, but the algorithm is still converges to onto the roots of 4. This happens because the fixed point theorem is a sufficient but not necessary condition. Even if the initial guess doesn't meet these criteria, it means the g prime at initial guess less than 1, the iteration can still converge, depends on how the function behaves and how the values mm, progress toward to the roots. For the For the second initial guess, okay, as you can see, the value of the G primes is at this initial guess is less than the one, and is meaning using the second fixed point form with this initial guess, okay, the iteration successfully converges to one of the function's roots. This is about the um, all the all the things that we have to know that for the fixed point iteration. The next numerical method for finding for root finding is Newton-Raphson method. It's a very fast and one of the fastest general purpose method when derivatives are available and making it ideal for problem when the speeds matter. However, just just as it can converge very quickly, it can also diverge very quickly if the initial guess is not suitable. It also provides a general way to rewrite any function, is meaning f of x, in the fixed point form. Okay, let's show the graphical interpretation of Newton-Raphson method. For example, if we consider this as an initial guess, first we draw the slope of the functions at the initial guess and extend this line until intersect the x-axis. The intersection points determine the new value, is meaning like as x sub 1. Next, we draw the slope at these points, okay, and extended this line to intersect the x-axis for giving the next value, x sub 2. This iteration continue until the x is close enough to the roots based on the criterion such as change between the iterative convergence or residual become smaller than a tolerance that defined by user. And what is the equations? If we write the tangent of these slopes, okay, we have AB over this length, okay, over AC. And if we are substitute by f of x and x, and then we rearranging, we get this formula. This is as a Newton-Raphson method. This is about the graphical interpretation that we understand we are using the slope at each point to iteratively approach to the roots of the function. Now we will look at the mathematical foundations behind this process. Assume we have an initial guess, is me x sub 0 or x sub naught, and a procedure that generate a sequence of and the process, okay, or the procedure is generate a sequence of improved solutions, okay? Because see, this is the point P as a root of this function, and this is the initial guess. And by each iterations, we improve our solutions, and we is converged to the roots of these functions. Then we expand a Taylor series about this point, x sub n. This is the Taylor series, and now we are evaluate these functions, okay, at xn plus 1. The next one, if the x sub n plus n, okay, is close to the roots of these functions, okay, then we can say this value is approximately as a 0. Also, the difference between the x sub n and x sub n plus 1 is small. And, uh, and this difference with higher power, okay, for example, power 2 or 3, approximately as a 0. Okay, again, if this point x sub n plus 1 is close to the roots, okay? Now we can, in the left side of the Taylor series becomes 0 because the value of the function at xn plus 1 is 0. And we have these two terms. And once we rearranging these equations, okay, we arrive at the Newton-Raphson method formula. Newton-Raphson method, like as the two previous method, as an iterative method. For this reason, we need the initial guess. X sub naught is an initial guess, and by plugging it into the Newton-Raphson formula, we find x sub 1s. In the next iterations, we are using the x sub 1s, okay, to calculate the x sub 2, and so on. This process continue until the iterative convergence or the change between iterations, okay, is less than the tolerance, or the residuals of the function is smaller than the tolerance that defined by users. Let's look at the previous examples, okay, and now we try to solve these problems based on the Newton-Raphson method. Okay, we know that the roots of this polynomial function is 1 and 4. The problem, we have to solve this, or we have to find these roots, okay, based on the Newton-Raphson method, and the initial guess is given as a 2. Uh, this is about the Newton-Raphson method formula. F prime x sub I. Okay, and the tolerance for the residual is given as a 10 to the negative 5. Okay, the first step, we are checking of the residual at the initial guess. Maybe this initial guess is close to the root and meet this criteria. For initial residual, it's meaning we are evaluate a functions, okay, at these points. The value is 2, and this is larger than the tolerance of the residual that defined by user. For this reason, we have go to the next iterations. For the first iteration, we need the x sub naught, the value of the function at x sub naught, and the first derivative of the function at these points. This is 2. The value of the function at this point, and the derivative of the function. The derivative of the functions, okay, for this function is a 2x minus 5. Now we are evaluate at point 2 or at initial guess. Once we solve it, the answer will be 0. Okay, how we can understand this answer is acceptable or no based on the information of the problems. The residual should be less than this value. This is the tolerance of the residual. For this reason, we will check the residual. As you can see, this is larger than the tolerance of these problems. This is the extra things. For example, if the problem asks us to find the iterative convergence for the first iterations, okay, we have, this is the general equation, xi plus 1 minus xi. This is for finding the iterative convergence for the first iteration. We have x of 1 minus x of naught is meaning 0 minus 2. This is the value of the x sub 1, and this is the value of x sub naught or initial guess is 2. Okay. As you can see, this value is not acceptable because the value of the residual is larger than the tolerance. Now we are going to the second iteration. For second iteration, we are using the value of the x sub 1 and x sub 2 is a x1 minus f of x1 over f prime x1. The value of the x sub 1 is 0 minus, this is the value of the function at this point. This means this is our functions. The answer is 0.8. This is the value of the x for the second iterations. Now we have to check the residual or to understand this answer, is it acceptable or no? Residual for the second iteration is meaning we have to find the value of the function at x sub 2. This value is 0.64 and still larger than the tolerance of this problem because the tolerance for residual in this problem is defined as a 10 to the negative 5. And we have go to the next iterations. Also, we can find the iterative convergence for the second iteration by these equations. X sub 2 minus x sub 1. The value of the x for the second iteration is 0.8 and the value of the x sub 1 is 0. And is zero point 0.8. Okay. For iterative convergence, also we need to know that the value of the tolerance. Okay. And if we continue continue this process, okay, after a certain iterations, okay, the algorithm is approach to the root one, okay, because the initial guess is given as a 2. The value of the x sub 1 is 0. X sub 2 is zero point 0.8. Okay. And once we continue, okay, the answer is approach to the root of the 1. This is the um, process, okay, for using the Newton-Raphson method. Okay, this is the solutions. Okay, first, second, third iterations. Okay, and this is the algorithm. Okay, we define the residuals. This is the Newton-Raphson's method. Okay, for these problems, okay, we require that both the residuals and iterative convergence, okay, meet the tolerance that defined by users. But for some type of the problems, maybe one of them is enough. Okay, these condition always defined by user or client, and for these problems, okay, after 7 iterations, okay, the we find the roots, okay, by tolerance of 10 to the negative 5, okay. But for the fixed point iterations, after 10 iterations, we find the roots by tolerance of 10 to the negative 3. For this reason, Newton-Raphson method is faster than the fixed point iterations. We can now interpret Newton-Raphson iterations as a general way to produce fixed point iteration for any functions, and geometrically, Newton-Raphson method uses tangent line to approximate the root, as we discussed earlier. Okay. As I mentioned before, Newton-Raphson is a fixed point method because uh, its iteration formula can be written as a x sub n plus 1 equal gx sub n. Okay, and by defining uh, this Gx, okay, each Newton-Raphson steps become a fixed point iterations, and the roots of x correspond to the fixed point of the Gx. And if you remember, for the fixed point iterations, okay, we are using the fixed point theorem to evaluate whether a given initial guess is expected to converge or no. And exactly we can apply for Newton-Raphson method in these parts. Let's look at these examples. We have these functions, the previous function, but the initial guess is given as a 0. Now we have to answer these questions. Any guarantee of convergence, uh, initial residual, first Newton-Raphson updates, and iterative convergence is and the rest. Okay, how to answer any guarantee of convergence? Okay, in previous slide we learned that Newton-Raphson method is a fixed point method, okay, because we can write the equation as a x sub n plus 1 equal gx sub n. Okay. Now we can apply the fixed point theorem to check by given initial guess. Okay. Is there any guarantee the solution is converges or not? Let's look at the solution of these examples. Okay, this is the function that we have. And this is the initial guess for these problems. Okay, and now we start to answer all the questions. Okay, with this initial guess, part A, any guarantee of convergence. Okay, this is the Newton-Raphson method. Okay, if we consider this is as a gx, we have this. Based on the fixed point iteration and fixed point theorem, the derivative of this gx should be less than 1. Okay, because this is showed, this part of the Newton-Raphson method is showing by G sub NR. NR is showing this is the Newton-Raphson's, okay? Based on the fixed point theorem, this one should be less than the 1. Now we take a derivative from the gx, okay? And the derivative of this part of the function should be less than 1. The derivative of the x is 1 minus the derivative of the f of x times this, okay, minus the derivative of the denominator is f double prime times f of x over f prime square. Okay, once we do the manipulations, okay, okay, first we make a common denominator. We will have a f prime square minus this one f prime square minus times negative times negative become positive over f prime xi square. Okay, this term will be removed. Okay, and the answer will be f double prime xi f of xi. This is the G prime for Newton-Raphson method. Okay, is meaning for applying the fixed point theorem for Newton-Raphson method, this value is mean the G prime should be less than 1. Let's check it for these functions with this initial guess. Okay, this is the function that we have, and the value of this function at point 0 is will be 4. The next one, we need to find the f prime. The first derivative is a 2x minus 5. The value at this initial guess will be negative 5 once we plug it. And the second derivative of these functions is 2 as a constant value. Now we are working with this value and plug it to this equation to check the guarantee of convergence, okay, based on this initial guess. The second derivative of the function, the value is 2. The value of the function at f of x is 4. And the first derivative of the function at point 0 is negative 5 to the power 2. The value is 0.32 and is less than the 1. And based on the fixed point theorem, okay, the algorithm will converge to the roots, okay, based on this initial guess. Any guarantee? Yes. This is the answer of the part A. For part B, we have to find the initial guess. And sorry, we have to check the initial residual. For checking the initial residual is meaning we have to find the value of the function at initial guess is a 0 to the power 2. This value is 4. We are working with the absolute value, okay? And this is about the value of the initial residuals. Find the value of the x for the first iteration or first update of Newton-Raphson method. For finding the x, okay, for the first iterations, we need this value. The initial guess is given 0. The value of the function at the x sub naught, and this is the first derivative of the functions. The value of the first derivative of the function at the initial guess is, and the answer is 0.8. This is the value of the x, okay, after for the first iterations. Now we have to find the iterative convergence. For the first iterations, we have x sub 1 minus x sub naught is 0.8 minus 0 is 0.8. This is the iterative convergence. Okay. Now For the residual of the first iteration, we need to find the absolute value of the function at x of 1. The answer is 0.64. Okay, this is about the answer of these examples. You can see the solution here, and this is the geometric interpretation we discussed earlier. We draw the slope of the functions, okay, at the initial point and extend the line until it intersects the x-axis, okay, and these intersections gives the next value, is meaning x sub 1. We then repeat this process and drawing a new slope at each point until the solution reaches to reaches a value that is sufficiently close to the roots. This is the some examples of pitfall of Newton-Raphson's. Okay, this is about the oscillation around the roots. Okay, the iteration jump back and forth near a root without converging. Okay, this is usually fixed by choosing a different initial guess. Another pitfall is no real roots. And the iteration may oscillate near a local minimum or maximum if there is no real roots in the region. And another pitfall is missing the intended root or root jumping. For example, we are looking for these roots. Okay, once we draw the slope for this initial guess, okay, we find we true in this parts, okay, and once we draw the slope at the x sub 1, okay, we are working in this part and we are finding another roots of the functions. For this reason, this is called root jumping. Okay, the next one is the order of convergence of Newton-Raphson method. And this value can be determined using the Taylor series. We start by expanding the Taylor series about the x sub n and then evaluate it at x sub n plus 1. If the x sub n plus 1 is close to the roots, this meaning root as a p, okay, then these terms is turned to the 0 and we can uh, we can write instead of x sub n plus 1 we can write the p, okay, and we get these equations, okay, and this is about the Newton-Raphson method. And by subtract, this is the equation 2. By subtracting equation 2 from equation 1, we obtain these equations. These quantities, okay, represent the error at iteration of n plus 1, and these quantities is show the error at the nth iterations. If you remember, for finding the rate of order of convergency, we have to write the two sequence error based on this equation is meaning the ratio of the error at n plus 1 and to the error at nth iterations. Once we rewrite or rearrange these equations, okay, the power of the error at nth iteration is 2, which indicates that the order of convergency for this method is 2. And this is about the constant value, okay? But just we are working on a order of convergency in this class. And we can say the order of convergency for Newton-Raphson method for the simple root is the quadratic. Okay. We learned that for a simple root, the Newton-Raphson method converges quadratically, which means is very fast. How, look at this one. Okay, this is as a simple root. But how about here? This is as a double root or multiple roots. Okay, for this reason, for multiple roots, the convergence is slower. For example, when the function has a double root, both the value of the function and the first derivative are zero at that point. For triple roots, okay, the value of the function for the first and the second derivative also zero, and also the value of the function at these points. For this reason, at the multiple roots, okay, the first derivative of the functions, okay, is zero. For this reason, the Newton-Raphson method converges more slowly than usual, okay, and uh, typically linearly instead of quadratically. Again, for the multiple roots. This is the summary of the Newton-Raphson method. Um, we learned that Newton-Raphson method is one of the fastest root finding method with quadratic convergence near a simple roots. It's especially useful when speed is important. However, Newton's Raphson methods require the derivative of the functions um, at that point, which can sometimes be difficult or impractical to compute for complicated function like as this. When computing the derivative is challenging, we can use the secant method as an alternative. The secant method approximates the derivative using two previous points instead of calculating it explicitly. Let's look at the secant method. Again, the secant method approximates the derivative of the function f of x in Newton is mean f prime x in Newton-Raphson method by using the backward finite difference to generate the iterations. This allows us to use a derivative free formula to update the next iterate and making the method practical when the finding the derivative of the function is difficult or the function become as an implicit. So that by substitute the backward finite difference, okay, to the Newton-Raphson method, we get the secant method or secant iteration formula. The only things that we have to know that for the secant method, for based on these equations, okay, we only need the value of the f of x at the at 2 points, okay, and we are not involving with iterations. For this reason, for the second method, we requires two initial guesses and it converges super linearly, okay? Because the power of the uh, error at nth iteration is 1.62. And if you remember, once the okay, is between 1 and 2, the order of convergence of the system is super linear. And this is about the secant method. And we start by supplying two initial guess, okay, x sub naught and x sub 1, and use them to calculate x sub 2 for the next iteration. We use the x sub 2 and x sub 1 to find the new value of the x sub 3, and we continue this process until the solution converges. And again, we have these two criteria to stop the iterations: the iterative convergence less than the tolerance, or residual less than tolerance. This is the geometric interpretations of the secant method. This is the two initial guess that we needed, okay, to find the next x. Let's look at the solution of the previous examples, okay, based on the secant method. Again, for the secant method, uh, we need to know that the two initial guess, okay, because we are not involving with evaluate a derivative of the functions directly. It means we are using the uh, backward finite difference. Okay, this is the function that we have. And we have to find the answer of the roots of this function based on the secant method. And the two initial guesses is given for these functions. 1.5. Okay, now we have to find the initial residuals. We have to answer these questions. Find the initial residual, find the value of the x for the first iterations, check the residual and iterative convergence. Also find the value of the x for the second iterations. Okay. Now we check the initial residual. For initial residual of the secant method, okay, we have to check both of the value of the function at these two initial guesses. The value is 2. Okay, we are working with the absolute value. Okay, the whole of these terms become negative 2, but we are working with absolute value. Another one is the value of the functions, okay, at second initial guess. Again, this value is negative 1.25, and we are working with absolute value. For example, if the tolerance that defined by user is 10 to the negative 5 for the residual, these two value is larger than the tolerance. And now we have go to the next iterations to find the x. First iteration. This is the general equations for the secant method. Okay, now we write for x sub 3 because x sub 1 and x sub 2 is given as a two initial guesses. We have x2 minus the value of the x sub 2 based on the information of the problem is 1.5. We have 1.5 minus the value of the function at this point, 1.5 minus 2, the value of the function at x sub 2 and x sub 1, okay? Once we find this value, okay, and plug to the equation, minus 2, the answer is 0.667. This means the value of the x for the first iteration based on the secant method is 0.667. Now we check the residual. We have to find the value of the function at this point. And the value is 1.111. This is the value of the residual for the first iteration. The next one is iterative convergence for the first iteration. The points for finding the first iterative convergence for the first iterations, okay, we have to use the value of the x for the first iterations minus the second initial guess is given. Okay, it's meaning we cannot work for finding the first iterative convergence. We cannot use the first initial guess. Okay, we have to use the second initial guesses, okay, for the secant method. For this reason, the value will be is again absolute value, okay, is negative 0.833, but the absolute is 0.833. This is the value of iterative convergence. Again, the point of the iterative convergence, okay, for the secant method, okay, for the first iterations, okay, we have the value of the x for the first iteration minus the second initial guesses, okay, that the problem is given. And now we are finding the second iterations, okay, for this method based on the secant method, okay. For second iteration, this is the value of the x for the first iterations minus the value of the function at this point. Once we plug this value of the function at these points, okay, we will have, okay, again, this is the value of the function at this point, and this is the value of the function at 1.5. Now, once we calculate the value of the x for second iteration will be 1.059. Now we check the residual for the second iterations. Once we calculate, the value will be 0.173, okay? And also iterative convergence for the second iterations is a difference in between the x for the second and first iteration, okay? Is meaning this value minus the value of the x, okay, for the first iterations is meaning this one. The value of the x for the first iterations. 667 and the value is 0.392. This is about the first two iterations of the sequence methods for this problem. This is about the sequence. See that these two initial guesses is given, okay, and then we plug it and find the first, second, third, and so on. This is the comparison between these four methods that we learn in this lecture and previous one. Okay, as you can see, Newton-Raphson method is the fastest method for finding the simple roots. After that, the secants. Okay, and this is about the bisections and fixed point iterations. The bisections method is the convergence linearly. Okay. Okay. Also, for finding a complex root, we can use the Newton-Raphson's method, but we replace the x with the complex number z, that is x plus iy, where the I is a imaginary units. Okay. The initial guess, okay, for finding a complex root should be as a complex number. Then we plug into the Newton-Raphson formula based on the z, okay, and perform the iteration as usual. After several iterations, the method converges to a complex root of the functions. Looking at these cubic polynomial functions, okay, is meaning these functions, okay. This function has three roots, okay. Two of these roots as a complex root and one of them as a simple root. If we try to find a complex root, the initial guess must be set up as a complex numbers. Okay, for example, once the initial guess is set up as a 2 plus 5 I, okay, after iterations, we find these roots, okay, is one of the roots of this function. But if the um, initial guess is set up as a simple number or as a real number, and the Newton-Raphson method will converge to the real roots of the functions. For example, if we set up the initial guess as a 2, okay, after certain iterations, we find these roots of the functions, okay? This is the point that we have to know that, okay, for finding a complex roots. Muller's method is another method for finding the roots of the functions. Is an extension of the secant method and good method for complex roots. And the rate of convergence is super linear because the value of the k is 1.84. For Muller's method, we need the initial guesses for finding the roots. This is the geometric interpretation of the Muller's method. There are some other methods. There are other methods we have for finding the complex root that we will not discuss in this class. This is the end of materials, okay, that cover on first exams, okay. For next chapter, we will learn how to solve the system of linear equations based on the mm, direct and iterative methods. Thanks for watching.